Alright, starting here with this video, we're going to start talking about coordination chemistry. This is our first real inorganic chemistry topic. Up until now, it's largely been reviewing general chemistry. So, a coordination bond is a type of bond that's formed by the donation of an electron pair from one species to another. A regular covalent bond is electron sharing. Let's say a carbon binds to a hydrogen, one electron comes from the carbon, one electron comes from the hydrogen. This is an electron pair donation, that both of the electrons in the bond are coming from the donating molecule. Right, so the electron pair acceptor is usually a transition metal or a transition metal ion. All our examples will be transition metals, but other metals can act as electron pair acceptors as well. The electron pair donor is a species with an unshared electron pair. Now usually this is something that has an oxygen, a nitrogen, okay, sometimes other elements as well. Most of the time, the most common examples, the donor atoms are oxygen, nitrogen, sometimes halogens. So this is called a ligand. All right, so the electron pair donor is called a ligand. Now, the resulting species, that is, the species is formed from the coordination, retains a charge, it's called a complex ion. So what are some examples of complex ions? Now, molecules that are neutral, like ammonia and water, both of these can act as ligands. We'll talk about that in a minute. Since these are neutral, ammonia doesn't carry a charge, water doesn't carry a charge, the complex ion will retain the charge of the metal ion. So let's say you have a +2 ion and you have water's coordinate to the complex ion, or ammonia's coordinate to the complex ion, and it will retain the charge of the metal. For example, when dissolved up in water, most transition metal ions will form complexes by coordinating water molecules. So for example, when most cobalt-2 salts are dissolved up in water, they will form this, what we call this hexaqualine. We'll get to the nomenclature towards the end. But they form this hexaqualine. Hexa means 6, aqua is water. Anyway, that is pink in color. Anytime you dissolve up, most of the time you dissolve up copper compounds in water, they form the hexaqualine. Those compounds tend to be blue, nickel salts tend to be green, but all these transition metal ions, and not just cobalt, copper, nickel, they all coordinate to water when you dissolve them up in aqueous solutions. Now, so back to this for a second. So like I said, ammonia and water are neutral. They don't carry a charge. So if we have a cobalt-2 ion, let's say, then the cobalt with the 6 waters is still going to carry the +2 charge. The copper with its 6 waters carries the +2 charge of the metal. The nickel with the 6 waters carries a +2 charge. So if you were going to have a neutral compound, let's say, then you would have to have anions to balance the charge. So if the cobalt with its 6 waters on it, if this has a +2 ion, we were going to have a neutral formula. Let's say we could have 2 nitrate ions out here to balance the charge, or we could have 2 chloros to balance the charge. Now, it's important for you to know that when you write these formulas, only the coordinated molecules are inside the brackets. What is outside the brackets is present for charge balance. So in other words, those nitrate ions, they're outside the brackets, they're not coordinated. So this is a cobalt, this is a complex ion that has 6 waters on it with 2 nitrates outside to balance the charge, but these are not coordinated. Same thing here. Even though chloride can be a ligand, it's not functioning as a ligand here because it's outside the brackets. Those chlorides are present for charge balance. So that's the first case. You can have neutrally charged ligands, you have a positively charged complex ion, you have anions to balance the charge. Now, it's also possible for you to have a negatively charged complex ion. Even though the metal may be positive, the complex ion may be negative if we're coordinating negatively charged ligands. So, for example, cyanide, if you know your polyatomic ions, and this is why it's important for you guys to know the polyatomic ions and the charges on them, you should know that cyanide is a -1. Therefore, we know that this complex ion contains iron 2. Why? Because plus 2 minus 6 makes a 4 minus ion. So here we have a negatively charged complex ion. Same thing here. This iron, or this compound, complex ion, contains iron 3, right? Because if the iron is plus 3 and every cyanide is minus 6, then plus 3 minus 6 gives you a 3 minus charge. Or one more example. If you see NO2, it's a very common ligand, nitrite ion. If you know your polyatomic ions, you know that NO2 nitrite is a -1 ion. Therefore, you have this complex ion contains cobalt 3+, right? Because plus 3 minus 6 gives you that 3 minus charge. So now, if we were going to have a neutral compound, we'd have to have positive ions out front to balance the charge. So if this is a 4 minus, then to write a neutral compound, we'd have to have 4 positive charges to balance the charge and make it neutral. We would have to have 3 positive charges here to balance the charge and make the compound neutral. Alright, so now in a few cases, the charge on the ligands will balance the charge on the metal ion, in which case you wouldn't have, it wouldn't be charged and you wouldn't have counter ions. So for example, if we had a cobalt 3 compound with 3 ammonias and 3 nitrites, alright, ammonia is not charged, but nitrite is a -1. So if this is plus 3, this would be -3. All the charges balanced, we would not have counter ions. Same thing here. If we were dealing with a chromium 3, let's say, I meant to have a 3 here. Okay, if we had 3 ammonias, let's say, and 3 cyanides, if this were plus 3, this isn't charged, but this is. So plus 3 and -3, and the charges balance. So let's talk a little bit about, different types of ligands. We already gave you the definition of a ligand. It's a species that has an unshared electron pair that can go and donate that pair to a metal ion. So we can classify ligands as monodentate, bidentate, tetradentate, and so forth. Okay, so monodentate, right? Mono implies 1. Monodentate ligands have 1 donor atom per ligand molecule. So for example, carbon monoxide, CO. Okay, you have an unshared pair on the carbon, unshared pair on the oxygen. It can function as a ligand. Alright, ammonia, and I've already mentioned now. There's an unshared pair on the nitrogen. Alright, ammonia is a very good ligand. There's many examples of coordination compounds containing ammonia. Water is another one. You have unshared pairs on the oxygen. NO2, which is nitrite. All right. You have unshared pairs on both the nitrogens and the oxygens. I'm going to talk about that in a minute. All right. Now this one you might never have heard of before up to this point. Maybe you have and maybe you haven't. SCN minus, that is thiocyanate. All right. Again, it has unshared pairs on the sulfur, unshared pairs on the nitrogen. It is capable of functioning as a ligand. Last one on my list here, cyanide, Cn minus. You have unshared pair on the carbon, unshared pair on the nitrogen. Okay, so one more time, it's important that you know some of these polyatomic ions that can function as ligands in these molecules. When you see NO2, the charge isn't going to be there in the formula for the complex ions. You're going to have to look at that and realize and say, okay, NO2, that's a -1. SCN, that's a -1. Cyanide, that's a -1. Okay, bidentate, bi means two, correct? Big surprise. So, bidentate ligands have 2 donor atoms per ligand molecule. For example, the first example, ethylene diamine. NH2, CH2, CH2, NH2. Ethylene diamine is very common, very good ligand. You have unshared pairs on both of the nitrogens. Okay, this is the way the thing is drawn out here. I've got a model of it here, right? And you can see that it goes nitrogen, carbon, carbon, nitrogen. Here's where it would coordinate, right? So this thing can bend and flex a little bit around the carbon, and carbon-nitrogen bonds. When it binds, it binds to the metal in 2 places and basically forms a 5-membered ring with what it's binding to. Okay. Another common example is carbonate. Right? You have 2 oxygens with -1 formal charges on them, 3 unshared pairs on each one. Right? Carbonate can be monodentate, but most of the time carbonate is bidentate. Now here's another one you might not have heard of, which is oxalate ion, which is C2O4 2-. Another very common ligand that's bidentate. We have 2 oxygens here with multiple unshared pairs on them, -1 formal charges. That's the way it would coordinate through those 2 oxygens. Acetate is another common example. You have an oxygen there with unshared electron pairs and a negative formal charge. Now here's one you for sure probably haven't heard of, and that's 2,2-bipyridine. Okay. Pyridine itself is just a single ring with the nitrogen in it. Bipyridine has 2 of these carbon rings, 2,2-bipyridine. Now, where does the 2,2 come from? Some of you may have had organic, some of you may have not have. When you number the carbons in a ring, you always start with the heteroatom. You start with the non-carbon atom, right? So that is the number 1 position. So that makes this the number 2 position. And you say, well, why can't I go around and 1, 2, 3, 4, 5, 6, why isn't that the 6th position? Because you always give it the lowest number that you can. So you come around, that's the 1 position, that's the 2 position. We do the same thing here. That's 1, that's 2. Okay, so that's where the 2,2 is coming from. We have 2 pyridine molecules joined at the CC bond. Okay. Now this thing is a little bit flexible. It can bend and flex. That's a CC single bond. Those 2 rings can bend and flex a little bit, okay, around one another, but the rings themselves are flat. It's all sp2 hybridized carbon. And we come down here, 1,10 phenanthroline, almost the same thing. All we've done is add 2 more carbons and that basically complete this ring. This one cannot bend and flex because you now have a ring here that's going to keep it from bending. Now, tridentate ligands have 3 donor atoms per ligand molecule. All right, so let's consider a common example: diethylene triamine. NH2, CH2, CH2, NH, CH2, CH2, NH2. Right. Now I want you to think a little bit. This is the common name for it. I want you to think a little bit about what this name is telling you. Diethylene triamine. An ethylene linkage is the CH2CH2. Right? So you have diethylene. That means you have 2 diethylene linkages, one here and one here. And it's a triamine. So you have 1, 2, 3 hydrogens. Or I'm sorry, 3 nitrogen donors. Right? You'd have unshared pairs on each of those nitrogens. Now, there's something else I want you to note here too, that carbon, or nitrogen rather, typically forms 3 bonds, right? So the nitrogens on the end are NH2 groups because they only have one other bond, and that's to the carbon. But the nitrogen in the middle is bonded to the 2 carbons, so it only has a single H. So the ones on the ends are NH2, the one in the middle is NH. And I've got a model here, almost too big to fit under the camera here, but a model of this, and you can see that it goes nitrogen, nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen. Okay, the nitrogens on the ends here are NH2 groups. Okay, the nitrogen in the middle is an NH group. Now, that's the beginning of kind of an unofficial nomenclature system for a whole series of compounds. So we went from ethylene diamine to diethylene triamine. So what would be the next one on the list? It would be called triethylene tetramine. So think about this. Triethylene means we have 3 ethylene linkages. One here, and one here. And we have tetramine rather. That means 4 nitrogen donors. 1, 2, 3, and 4, right? So triethylene tetramine. This also goes by the name 2,2,2-tet, and you'll get one guess as to what the 2,2,2 stands for. That's a 2 carbon linkage, 2 carbon linkage, 2 carbon linkage. Okay. Chemists have been particularly innovative about designing new ligands. I mean, these are just a couple of examples, right? So this is 2,2,2-tet. There's also a 2,3,2. If you want to guess what that stands for, then that means we would have a 3 carbon linkage in the middle. So that would be 2,3,2. Or we could have a 3 carbon linkage here and here. In this case, it would be 3,2,3-tet. Or we could even have a 3,3,3-tet. All right. Now, another class of ligands comes from, I think these are important, and I think that you need to know about them, that some other ligands have come about by basically, instead of having all nitrogen donors, they're basically grafting acetate groups onto an ethylene diamine. So we take off one of the hydrogens on the ethylene diamine and replace it with an acetate group, right? So that NH, NCCH, that's our ethylene. We would be NH2. Here we have one H. We've taken off the other H and added this acetate group, CH, CH2, COO minus. Okay, so that would be ethylene diamine diacetate, right? diacetate, meaning that we have 2 acetate groups, right? And this has 4 donor atoms. The two nitrogens in the ethylene diamine still have those unshared pairs. They're going to donate. And then we have 2 unshared pairs on the oxygen atoms on the acetate groups, right? So we're going to have 1, 2, 3, 4 donor atoms. That makes it a tetradentate ligand. Now here's the last one I think that you guys need to know. Hexadentate is going to have 6 donor atoms, okay? So the classic example of this is ethylene diamine tetraacetate, which goes by the abbreviation EDTA. And this one you might have heard of before. It's kind of an important molecule. All right, so what we've done is we still have our ethylene diamine, and now we have grafted 4 acetate groups onto this molecule. So how many donors are we going to have now? 1, 2, 3, 4, 5, 6, which is what makes it hexadentate. So basically then, a lot of your transition metal compounds have 6 octahedral compounds that have 6 donor sites. So this thing is going to wrap around a metal and completely encapsulate it, basically tie up all the coordination sites. It's used for other things, and for example, kelometric titrations, because it, like I said, it wraps around and encapsulates a metal and reacts with the metal on a 1-to-1 basis. All right. So now let's talk about ambidentate ligands. All right. So what are ambidentate ligands? Ambidentate ligands are ligands that have more than one mode of attachment. So for example, nitrite, which I previously used as an example, that can actually attach through the O or through the N. There were unshared pairs on both a nitrogen and an oxygen. So here, if this is your metal center, let's say, and a metal center here, then it can bind through the N, or it can bind through the oxygen. Okay. Cyanide is another example. It can bind through the carbon, or it can bind through the nitrogen. Okay. Thiocyanate. Okay. Here's still another one. All right. It has unshared pairs on the sulfur and the nitrogen. It can bind through the sulfur, or it can bind through the nitrogen. All right. So we've gone over a little bit here. All right. So what are coordination compounds? What are complex ions? What's a ligand? What's the difference between a monodentate, tridentate, tetradentate? What are ambidentate ligands? 2 modes of attachment. So in the next video, then we'll go in and talk about nomenclature of coordination compounds.